Hi everyone, welcome to the first video tutorial of SBI4U. We're going to begin with obviously the first unit of the course, which is titled Biochemistry. I've broken this unit up into three separate parts just to keep it a little bit more organized for you. It is a huge unit. We cover a lot of information in here. It's a challenging unit, so I feel that breaking it up a little bit helps. So we're going to begin with part one, which is basic biochemistry. It's a little bit of review of some basic chemistry, perhaps some new chemistry for those of you who haven't taken grade 11 chemistry. And then we're going to move into a study of the biochemical molecules that make up all of our cells and make up all of living things. And that will be the focus of this first part. After that, we'll move into part two. We'll be looking at cell structures, which is primarily a review from earlier science courses, but we'll take it a little further and look at some of the more intricate functions of the parts of the cell. And in the final part, part three, we'll be looking at thermodynamics, which is the study of energy transfers within the cell, the creation of energy out of food molecules, or the breaking down of food into energy, in other words, and the production of energy by building up molecules. And we'll end it off by looking at enzymes. We'll study how enzymes work and what their structure is all about, and we'll be doing a summative lab on enzyme functions. So let's move into part one. Hold on. It's playing. In order to understand biochemistry, you do have to have a little bit of chemistry knowledge. So we're going to take this all the way back to atomic structure. Here's a model of the atom. This is the planetary model of the atom. Our model of the atom is evolving as we learn more about some of the smaller subatomic particles, but the basic atomic structure is that the atom is made up of a nucleus, and in the nucleus we find protons and neutrons. Protons have a positive charge, neutrons are neutral. These are the particles in the atom that have a lot of mass. Spinning around the nucleus are these little tiny electrons. Remember that electrons are negatively charged, and they spin around within a path or an orbit. The quantum mechanical model, which is something that scientists like Einstein worked on, allows us to predict where an electron would be in relation to the nucleus. You need to remember that in an atom, the nucleus is very, very tiny. It's a small part of the whole atom in terms of space, but it has a lot of mass. And then most of the atom is this empty space around the nucleus in which you find one or more electrons spinning around rapidly within their orbit. The location within the atom that you would find an electron, or we would predict an electron to be found, is called its orbital. So again, just to review atomic structure, we have the nucleus with the protons and the neutrons. And this is where the mass of the atom exists. And then we have these little negative electrons spinning around in their orbits, in the orbitals, around the nucleus. When we study chemistry, we are looking at the elements that make up molecules. So recall from earlier studies that elements are substances, they're pure substances that are made up of only one type of particle. So if I'm holding a piece of iron in my hand, all I have are iron atoms. And the most useful information that we can get from the periodic table about an element are its mass number and its atomic number. So what I have on this slide is a way that we can symbolize an element. It's called notation. It's element notation or atomic notation. And this might be something new for a lot of you, but basically the X right here just indicates the symbol of the element, and then to the left side of the symbol, as a superscript, you would write the mass number taken from the periodic table, and as a subscript, where Z is right here, that would be the atomic number. And so one of the things that you learned early on in your study of chemistry is that the atomic number is equal to the number of protons in the element, and the mass number is equal to the number of protons plus neutrons. So if you want to calculate the neutrons in an element, you would take the mass number and subtract the atomic number. So you're taking the total mass of the atom, subtracting the number of protons, and that leaves you with the neutrons, because the sum of the protons and the sum of the neutrons equals the mass number. So this is a really useful way to just simply show an element and show its two most important pieces of information to us, its mass number and its atomic number. So here's an example of atomic notation for a sodium ion. I say ion because you can see that there's a charge right here. So we put the symbol in the middle, sodium, and the mass number for sodium is 23. The atomic number is 11. You would take this from the periodic table. The fact that there is this plus sign here tells me that this is a sodium ion. Not a sodium atom, but an ion. So it's a charged sodium atom. Sodium has one valence electron. It has one electron in its outermost shell, and this would be the one electron that sodium would want to give away. When it gives away a negative electron, it takes on a charge of +1. And so that's why this plus sign is right here, and that indicates that +1 charge. Now, in biology, one of the unique features of elements that we use to our advantage are called isotopes. If you've taken chemistry before, you probably should remember what an isotope is, but if you don't have that chemistry in your background, this may be a new word to you, unless you're a fan of The Simpsons, and then you've heard of isotopes before. So just take a moment and see if you can remember what isotopes are, and if you don't know, there's a clue here. Why would The Simpsons have a baseball team called the Isotopes? Think about what the main industry was in Springfield. Okay, do you give up? I'll tell you what an isotope is. Isotopes are atoms of the same element that have different masses because they have different numbers of neutrons. And sorry, I have a typo here in my text, but isotopes are atoms of the same element that have different masses because they have different numbers of neutrons. So for any element, there are infinite, huge number of atoms of that element on the planet. And if we take a sample of that element, within that sample, there would be different versions of the atom of that element. They're all the same element because they have the same number of protons, but they'll vary in terms of the number of neutrons in the nucleus. For most elements, there's one type, one isotope that is much more common than the rest, and the other isotopes tend to be more rare. So I'm going to show you a couple of common examples of some really common elements on Earth that have isotopes that we're familiar with. We'll begin with hydrogen. Hydrogen has 3 isotopes, so think of it as there's 3 versions of hydrogen. There's protium, deuterium, and tritium. Protium is the most common form of hydrogen, and this hydrogen has just 1 proton. There would be 1 electron spinning around that nucleus, but notice there are no neutrons. So for this one, the mass number, the number of protons plus neutrons, is 1. The atomic number is also 1 because there's only 1 proton. But there are some rarer forms of hydrogen called deuterium. And in deuterium, there's a proton and a neutron in the nucleus. So the mass is now 2. The atomic number is still 1 because there's only 1 proton. So this is still hydrogen. It's just it's a little heavier than the protium version, the protium isotope. The third isotope is very rare. It's called tritium, and it has 2 neutrons. So its mass number is 3, and its atomic number is still 1. So again, it's still hydrogen. It's an isotope of hydrogen, and it's a lot heavier. And what's really interesting about isotopes from a biology perspective is that the bigger the difference between neutrons and protons in the nucleus, the more unstable the nucleus is. So think of it as being unbalanced. It doesn't have the same number of positive to neutral charges, and it has a very heavy nucleus. And that plays a really important role to us as biologists, And I'm going to ask you to learn about that independently using your textbook. We call these isotopes radioisotopes. And that's the Springfield connection to the Springfield isotope baseball team. If you remember, there is a nuclear power plant in Springfield, and that's the relationship to these isotopes that have these very unstable nuclei. So another common isotope that we use in biology is the carbon isotopes. Carbon, like hydrogen, has 3 isotopes. There's carbon-12, carbon-13, and carbon-14. And these don't have a name like hydrogen did with deuterium, tritium. These isotopes just simply go carbon-12, carbon-13, carbon-14. The 12, 13, and 14 tell us the mass of the isotope. So carbon-12 means it has a mass of 12. So it has 6 protons and 6 neutrons. We know that carbon is atomic number 6. So it's going to have 6 protons, no matter which isotope of carbon it is. But if it's carbon-12, that tells me that it has 6 plus 6 in its nucleus, so it must have 6 neutrons. Carbon-13 has 13 particles in its nucleus, so it has, again, 6 protons because it's carbon. That will never change. If you change the number of protons, it's a different element now. So these are all carbon. So this one, carbon-13, has 7 neutrons. Carbon-14 still has the 6 protons, but to make 14, we would have 8 neutrons. And carbon-14 is very rare. You can see less than 0.1% of all carbon atoms on Earth are this version of carbon, this isotope, carbon-14. And carbon-14 is really important to a certain branch of science, and that's something you can read about in your text.